we have seen the chain rule. So for example, just to refresh our memory, if we have to take something like the derivative of cosine of the third root of x, then the way we did it was we designate an inner function. In this case, the inner function is cubed root of x. We think of it as y, and we ask what the derivative of cosine of y is. And the derivative of cosine of y is negative sine of y. So negative sine, we never write y. We actually write cubed root of x. And we follow this up with the derivative of what we designate as y, the derivative of cubed root of x. Cubed root of x is x to the 1/3, so its derivative is 1/3 x to the negative 2/3. And that's our chain rule. Today, we would like to look at examples that involve more than one composite. So let's begin with one such example. So let's say that we want to take the derivative of the sine of e to the x cubed. So here, actually, when we try to designate an inner function, we're faced with two very good choices. The first choice is to just take x cubed. Okay, so that could be the inner function. The other choice is to actually take the whole e to the x cubed as the inner function. And in general, you will see that our strategy will be to take the largest possible as the inner function. So we're going to take the e to the x cubed and designate it as y, which means that we're looking at sine of y, and the derivative of sine of y is simply cosine y. So we write cosine of e to the x cubed. The thing that changes slightly here is that we're not going to execute the differentiation in just one step. We're going to just say that we need to take the derivative of the inner function. So I'm going to write the derivative of e to the x cubed, and I'm going to finish it in the next step, because now what I have is the derivative of a single composition. So in some sense, I'm still carrying with me cosine of e to the x cubed. And but I'm focusing on the derivative of e to the x cubed as if this was the only problem that we had to deal with right here. And the derivative of e to the x cubed, so now we designate x cubed as our inner function. So we're faced with e to the y. The derivative of e to the y is e to the y, meaning e to the x cubed. And we multiply by the derivative of what we designated as y, meaning the derivative of x cubed, which is 3x squared. So in some sense, we can see that we did what we're used to doing twice. And this thing that we found here was simply this. So it was as we had to do another differentiation of the same type. Okay, so why don't we do another example? So let's take secant of e to the tangent x. Okay. Again, spend a little time to pause the video and try to do this yourselves. And let's take a look at it together now. So we're going to designate e to the tangent x as our inner function. So we're looking at secant of y. The derivative of secant of y is tangent of y. So I'm going to write tangent of e to the tangent x because that's what we designated as y, times secant of e to the tangent x. And we're going to multiply by the derivative of what we designated as y. And so now it's as if our problem is to do just this. We just ignore, we still have to write it, take it with us, tangent of e to the tangent x times secant of e to the tangent x times, and we think of this as e to the y. So this will give us e to the y, meaning e to the tangent x times the derivative of what we designated as y, which is simply secant square of x. And that completes this problem. Now, let's do this one. 2 to the 3 to the 4 to the x. Okay, this looks kind of funny. So again, pause the video and try to actually do this problem. So the question is, and maybe we can use a little bit of visualization here, what we're going to consider as the inner function. And here's what we're going to consider as the inner function, which means that the whole thing is going to be considered to be 2 to the y, right? And the derivative of 2 to the y is 2 to the y ln 2. So what do I write here? I write 2 to the y, of course, y is 3 to the 4 to the x times ln 2. And then I want to take the derivative of 3 to the 4 to the x. Okay, which means that we're starting from the beginning. This is a new problem. And what do we have? We have 2 to the 3 to the 4 to the x times ln 2. And here, if we focus now simply on 3 to the 4 to the x, then we have that y for us will be 4 to the x. So we're looking at 3 to the y. So the derivative of 3 to the y is simply 3 to the y, meaning to the 4 to the x times ln 3. And we have to follow this by the derivative of 4 to the x. And finally, this is going to be 2 to the 3 to the 4 to the x times ln 2 times 3 to the 4 to the x times ln 3 times 4 to the x times ln 4. Let's take a look at a different example. So imagine that we have something like cosecant of the square root of sine x. How would we do this one? Again, pause the video, try to do it yourselves. We're going to think of the inner function as square root of sine x. So we're looking at cosecant of y, and the derivative of cosecant of y is negative cosecant, or negative cotangent. It's the same thing, cotangent of square root of secant x times cosecant of square root of sine x. And we need to multiply by the derivative of the square root of sine x. And now we do this as a separate problem. And we will get negative cotangent of square root of sine x times cosecant of square root of sine x. And here we designate sine x as y. So we will get 1/2 square root of sine x times the derivative of sine x, which is cosine x. And let's do one more example here. And for our last example, let's choose something like 5 to the cotangent of 6 to the x. Okay, so let's see how we would do this. We're going to designate cotangent of 6 to the x as our y. So this will be 5 to the y times ln 5 times the derivative of cotangent of 6 to the x. And what is the derivative of cotangent of 6 to the x? So now we focus simply on this part. So it's as if you're looking at cotangent of y. And the derivative of cotangent of y is negative cosecant square of y times the derivative of what we designate as y, which is simply 6 to the x times ln 6. Notice that in the previous example, we could have done this in simply one step. We took one more step here, maybe because of the complexity of the, I could have just written here directly 4 to the x times ln 4, but I took one more step to do it, which means that nobody can rush you. You can take as many steps as you like while doing this. But one thing that you can see in common of all these considerations is that we always try to take the largest possible expression as our inner function. This doesn't mean that if we wanted to take the smaller expression that we wouldn't have been able to do that. No, but this is just the strategy that we decided to choose for this kind of situation. And that's all. I hope you enjoyed this video.